another episode of Mr. Avila Physics. Today we're going to be talking about power. By definition, power is the rate at which work is done. In other words, it means how fast can something do work, right? So the how fast part means how long does it take you. So power would be equal to work divided by time. But we also know that work is equal to the change in energy. So we can also define power as how fast is energy being transformed or changed. Now, in formula form, this will look like power is equal to work over time, which is equal to change in energy over time. Now, there's another formula, okay, that we can also kind of change from here. Now we know that work is equal to force times distance over time. And this part right here, we know this from previous videos. This part right here is average velocity. When the velocity is constant and there's no acceleration, then this is distance over time. So we can also say that average power is equal to force times average velocity, where this velocity needs to be constant, okay? Constant. All right. Now, what are the units of power? Now, according to the formula, the units of powers will be joules per second, okay? How much energy can be transformed into mechanical energy per unit time, right? Power is equal to work over time. Work is in joules, time is in seconds. So the standard unit of power is joules per second, but instead of saying that, we have a special name for it, and that is the watt, where 1 watt is equal to 1 joule per second. Now, you may be familiar with the unit of watt, right? Talking about light bulb or heaters or some speakers that give the output in watts. But sometimes for machines or engines or motors or anything like that, we have another unit that you might also be familiar with, and that is the horsepower, right? Where 1 horsepower is equal to 746 watts. All right, let's try this example. A 60-kilogram jogger runs up a long flight of stairs in 4 seconds. The vertical height of the stairs is 4.5 meters. Estimate the jogger's power output in watts and horsepower, and how much energy did this require? All right, pause the video here, try this example, and see if you can come back in a couple of minutes for the answer. All right, welcome back. Okay, so in this question, they're asking us to find the power output, and we know that power is equal to work over time, which is equal to change in energy over time. In this case, the jogger went up a long flight of stairs, so his potential energy changed because he is higher than when he started from, right? He's at a higher position. So the change of energy will be mgh over time. So this is going to be equal to 60 times 9.8 times the height, 4.5, divided by 4 seconds. So the power output is going to be equal to 60 times 9.8 times 4.5 divided by 4. 661.5 watts, which is the same thing as 0.89 horsepower. Now for question B, how much energy did this require? Well, I know that power is equal to change in energy over time. So energy is going to be equal to power multiplied by time. So it's going to be equal to 661.5 watts multiplied by 4 seconds. This is going to give me 2,646 joules of energy, which is the same thing as if you calculate this part right here, the potential energy of the jogger. Okay. All right. And here now, in reality, the jogger spends a little bit more than 2,646 joules. This is if our bodies were 100% efficient and all the energy was used efficiently, then yes. But in reality, we used energy to breathe and pump our heart and flow blood and fluids all through our body and raise our temperature when we exercise. So there's a little bit more energy being used than just this. But for our purposes, we're going to assume that our bodies work very, very well. All right. Okay. Now let's take a look at this example. Calculate the power required of a 1,400 kilogram car under the following circumstances. When the car climbs a 10-degree hill at a constant speed, remember that steady means constant, at a constant speed of 80 kilometers per hour. And when the car accelerates along a level road from 90 to 110 kilometers per hour in 6 seconds in order to pass a different car. Now for both of these cases, consider a frictional force of 700 newtons throughout the entire problem. All right, pause the video here, take a couple of minutes and see if we can come up with an answer. All right, welcome back. So for the first part, okay, we have that a car is climbing up a hill, right? Now, if the car is moving at a steady or constant 80 kilometers per hour, then we know that the net force acting on this car has to be 0 because the velocity is constant. So if we draw our free body diagram, we're going to have Wx, we're going to have W, we're going to have a frictional force, and we're going to have the force of the engine. So our net force is going to be equal to F minus Wx minus friction force, and this is going to be equal to 0, which means that our net force is going to be equal to Wx plus friction force. This is going to be equal to mg sine theta plus 700. And that means that F is equal to 1400 times 9.8 times sine of 10, okay, plus 700. Force is equal to 3082.5 newtons. So the power required by the engine needs to be force times average velocity. So this is going to be equal to our force times our average velocity. Now we have to be careful when we input information into our formulas. We have to be very careful with the units, okay? If we're working with newtons, then we have to work with meters per second. So I have to change those 80 kilometers per hour to meters per second. And in order to do that, I have to divide by 3.6, which means that the power required of the engine is going to be equal to that times 80 divided by 3.6. That gives me a power output of 68,499 watts, which is approximately 91.8 horsepower. So, okay, this is a pretty good size engine, right? Close to 100 horsepower engine. All right, cool. All right, so now let's answer question B, and I'm gonna erase this so that I have space to answer question B. All right, in question B, we have the car that is on a level road and is accelerating from 90 to 110 kilometers per hour in 6 seconds in order to pass another car. So here we do our free body diagram. This is weight, this is normal force, this is the force provided by the engine, and this is the force of friction. So I know that net force is going to be equal to F minus the force of friction, and this is going to be equal to mass times acceleration. I know that it's not equal to 0 because the velocity changes from 90 to 110. So in order to be able to find our net force, then I need to find acceleration. So let's find acceleration. Now from previous units, I know that final velocity is going to be equal to initial velocity plus AT. Final velocity is going to be 110 divided by 3.6. Why are we dividing by 3.6? So that we can change our units from kilometers per hour to meters per second. From here, we can get a value of acceleration. This is 30.56 is equal to 25 plus 6a. So acceleration is equal to 0.93, which means that our net force is going to be equal to F minus friction, and this is equal to 1400 times 0.93. From here, I find F, the force necessary by the force that the engine needs to apply on the car. So that gives me approximately 1,996.3. And so the power supplied by the car is force times velocity. But which velocity should I use? Should I use our initial velocity, 90? Should I use our final velocity, 110? Or should I use the average of the two? Well, since we want to pass the car, since we want to pass another car, then our car should be able to supply the maximum amount of power necessary to pass. And the maximum amount of power necessary to pass comes with our maximum velocity, which is 110 kilometers per hour, divided by 3.6, and that should give us the average. So the power necessary by the car is going to be equal to 1996.3 times 30.56, and this is going to be equal to times, it's going to be equal to about 60,997.9 watts, which is approximately 81.8 horsepower. Right? All right. Hopefully you were able to solve these examples. Now, on a previous slide, I talked about how our bodies weren't 100% efficient. What does it mean to be efficient? What does efficiency mean? Okay. Efficiency is defined as the ratio of the power output to the power input. Okay. How much power is supplied to the engine versus how much power can the engine can produce. Okay, so that's power in and power out. So for example, if we're talking about a car, you provide it with gasoline, right? Gasoline burns, and not all of that is being used to power the car. There's a lot of waste on gasoline engines, right? A lot of it just goes to heat up the engine. A lot of power is waste and it goes up the exhaust pipe, and only very little actually moves the car forward. So to define efficiency, we simply divide output power divided by input power. Okay. Now the efficiency is always less than 1. There you cannot produce more power than what is put into the machine, okay? Because energy cannot be created. All right, so, okay, that is efficiency. There is no machine is 100% efficient, and scientists are trying to develop and find ways to reduce energy waste to make machines more efficient. Well, this is power and efficiency. Thank you all for watching, and I will see you next time.